I have to say a few words about here. Actually, I use a property which is called the even property of the Dirac scalar function. Yeah. The Dirac scalar function, when delta of minus t is equal to delta t. You can go back to our definition of the impulse function. We can go to prove that, and then so this one delta of t minus tau actually is equal to delta of minus tau minus t. Okay, now you can express by this one, and then this is equal to delta tau minus t. Okay, by using the even function property of Dirac scalar function. Okay, and so by our definition of scalar function, this is empty. So any questions? And to draw the g of t minus tau, you have to know that g of t minus tau can be written as g of minus of tau minus t. So and so this one is a time translated version of this function, g of minus tau. But g of minus tau actually is the mirror image of g of tau by the y-axis. So originally, if you had g of tau like this one in white color, then g of minus tau is this one in yellow color, and then you shift t, right here. So this is t here. You shift right shift, and so this is g of t minus t. This is the way I described for you. Okay, so now I have to prove the convolution theorem. For Laplace transform. Translate f of t and g of t and piecewise continuous. Real infinity is Laplace transforms f of x and g of x exist for all real power greater than sigma 0. Okay. So we are given two piecewise continuous functions, f, t, and g. And their Laplace transforms, f of x and g of x, exist for all complex variable x whose real part is greater than sigma 0. In this case, then the Laplace transform of real convolution exists for all real part and sigma 0, and the Laplace transform of f and g product of the Laplace transform of f and the Laplace transform of g. So in time domain, we have convolution, but in S domain, we have product. Okay, so we assume that x is real. The variable is real, and then here. Okay, this is for convenience because we haven't discussed complex integration yet, right? We haven't. So I just assume that the variable x is real, and as I mentioned before, that if this is true, then then for any complex value of x with real part greater than equal to 0, also true. Okay. Then now we try to so we try to evaluate this thing. Now by definition, okay. Now this is FP and the E minus SP dP and the G of P minus P. So so we in here we integrate T first and T, right? But now we want to integrate T first and then P. So that the integration, as we discussed before, here is from here to T. Now if we change the order, then we have to integrate from P to infinity. And this is G minus P, T minus P. So we split P into P plus T minus P. Okay? So I split T into two parts, P plus T minus P. So minus SP goes here, minus S times T minus P here. Okay, and then GT here. If you don't know what is the proper integration, lower limit, upper limit, the best way is to just draw. Okay, so you have this is T and this is P. Okay. All right, and for P, the integration is here. This is P equal to T So the equation here, because t is from 0 to infinity. Now, if you want to integrate t first and then p, so you fix p. When you fix p, the t will integrate from p to infinity. Okay, so you will integrate in this direction, the horizontal direction here, instead of the vertical direction. So you have to integrate from p to infinity. Is that okay? Alright. And so from here, so by taking and again the order of integration is changeable. Okay, by Rubin's theorem. Okay, and for here, okay, we can. This is equal to. So we just let t equal to tau equal to t minus p, because in here p is a fixed parameter. So with this one, we have from 0 to infinity, okay, and this is g tau, b tau, right? So by change of variable, okay. So now we have p tau. Okay, this integral is independent of p, right? So right here, and so the double integral becomes to be fully separable, and this one is equal to f of x, and this one is equal to g of x, and like that. So this is the convolution theorem. Alright, so let's take several examples. Right, so we know the first transform of a function h of t is 1 over x times x minus a. So we consider that f of x equal to 1 over x and g of x equal to 1 over x minus a. Okay? So h of t, which is the inverse Laplace transform of h of x, and this one, okay. So h of x actually is a product of f of x and g of x, and by convolution theorem, the inverse Laplace transform is f and this convolution. Okay, by the convolution theorem. Right? So by the convolution theorem, we know that And here we know f of t, 1 over x, f of t is constant, right? It's a constant. And the g of t is the exponential function, at. Okay. So we have f of g here. So h of t is the convolution. Zero. So we just reduce maybe better. Okay. So okay. So this is equal to okay. Of course, you can do this by partial fraction, right? You can expand this fraction by using a partial fraction. So you have two terms. So of course you will get to the same result. And over here, I just want to use the convolution theorem. This is what I did. Any questions? Alright, Volterra integral equation of the second kind is that yt minus t yt sine right. So we have the Volterra integral equation. So yt satisfies this integral equation. And we know this is actually, this part is just the convolution of y of the solution and the sine. Solution. So now it's quite natural to apply the convolution theorem. Right? It's quite natural. If you don't apply the convolution theorem, then it would be a hard problem for you. So now by taking Laplace transform on both sides, we have y of x here minus y of s and the Laplace transform of sine function. What is the Laplace transform of sine function? Okay, so sine t is equal to, and the t, the Laplace transform function t is equal to 1 over s squared. Okay. Now, and this one, as we know, this is equal to 1 over s squared plus 1. Okay, so now y of x 1 minus 1 equals, okay. So this implies that y of x is equal to s4. Okay. Because this comes to s squared divided by s squared plus 1. Okay, so now we have this one. And you have 4. So y of t becomes 2t plus 3 factorial to okay, and you solve your problem quite easily. Any questions? So sections. Alright, so we finished chapter 6. And now we will go back to chapter 5 to discuss power series solution of differential equations. Although the existence and uniqueness theorem of differential equation tell us that there exist unique solutions. If you are given an s-order ordinary differential equation with initial conditions at some point, but to get an explicit solution, we find that we usually have to resort to linear ordinary differential equations with constant coefficients. Okay, so usually, or if the coefficients are not constant, then it will be a kind of very special kind. Right? And so we would like to know that we have a more flexible way to find solutions. Okay, and indeed we can find solutions by using modern computers. Right? And so we are talking about the serial solutions of all these. Okay. And the spatial functions. Okay, now this chapter actually is a long chapter, but because of the time limitation, I just take a couple of topics to mention in this semester. And so if you really need to solve ODEs later on in your career by series, then you have to go back to read through this chapter by yourself. Okay? So my main purpose is to introduce the power series method. And before doing so, I have to review some of the ideas we learned in calculus, especially about sequence of functions and the series of functions. Okay? I'm talking about sequence of functions and series of functions, not sequence of numbers or series of numbers. You know, I'm talking about sequence of functions. All right. So the first concept that I want to introduce is about upper limit of a sequence. All right. So here, sequence. I'm referring sequence of numbers. All right. So I want to introduce upper limit. A real sequence an may converge or diverge. Okay, so real sequence means that a sequence of real numbers. Okay, so A sub n are real numbers. Okay, and any such as real sequence may converge to a limit or diverge. And it's a very troublesome subject, right? When you learn calculus. Now, but sequence always is an upper limit. So upper limit always exists. And so that is very useful. And how to define that? Well, it's defined to be the upper limit makes the soup. So the notation is called soup. For n goes infinity, the n is defined to be the limit of the suprema okay. So what is that meaning? And this number, which may be infinity minus infinity, or any number, or real number. All right. So now the suprema, you know, the suprema of a sequence is the least upper bound. Remember, right? In calculus, we define suprema is the least upper bound. Okay. So remark. Suprema or just the suprema of a m from n to infinity, okay, is the least upper bound of am from greater than Now, you can see that the suprema, the sup, okay, okay, so when n equal to 1, the sup is greater than or equal to the suprema of n greater than 2. So as n goes on, the supremum will going down. Okay? Becomes smaller and smaller and smaller. You know why, right? Because you have in here you have more numbers to take this upper bound. With this one you have one less, right? In numbers. You begin with n greater than equal to 2. But here it begins with n greater than equal to 1, right? Begin with 1. This is with 2. Okay? So the supremum, well, in principle, decreasing. So you have a decreasing sequences. Any decreasing sequence has a limit. Okay? And the limit can be minus infinity, of course. So that's limit. Okay. Always. And b infinity minus b all real number. Okay, so let's take some examples. 1, an is equal to n. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. N equal to n. Okay, in this case, the sup is the limit sup m. Okay, or say am sup m. Okay, here. Now, this is unbounded, right? If m greater than n, it will go to infinity. So this is the limit. M goes to infinity, and here is infinity. Because every sup is infinity. So of course the limit is infinity, okay? So you get infinity here, right? Second. Minus n. Okay, so the sup so am is minus n. Now, you want to take the suprema, right? And n is greater than or equal to n. So the suprema is what? Minus n, right? The biggest one. Minus n. Because minus n is bigger than minus plus n, right? So you have minus n here. Is that okay? sequence here you have minus n plus 1, minus n plus 2, minus n plus 3. So this is going down, right? So what is this upper bound? Minus n. Is that correct? Upper bound, right? Upper bound. So this upper bound of this sequence is minus n, the head. And so this is minus infinity, of course. As n goes infinity, this is going to minus infinity. So in soup is minus infinity. So you can see the wide range, right? In soup, sometimes it goes to infinity, sometimes it goes to minus infinity. Okay. Very wild, right? This one, on the way. Of course, in this case, the name is soup. And m is 1 over m. And then n. So what is the supremum? 1 over n, right? The head, right? The head is the supremum. And this goes to 0. Alright, so this you have so I just take this example to illustrate the behavior of upper limit. Okay, so the upper limit, the notation is called the soup. Okay, sometimes I will say in soup, or sometimes I say upper limit. Oh, poor cow. I have a meeting to attend. Okay. Thank you. Yeah. Okay, I have to stop here.